So, good morning and happy Wednesday to everyone. I hope everybody's doing well. As we're slowly reaching the end of the part where we're giving new material here. And as you will see on a Blackboard, I have posted all three last assignments. Please don't get confused. Make sure you look at the dates and do the correct assignment. So today's assignment for Friday is homework 13. Friday's assignment for Monday is homework 14, and Monday's assignment for Wednesday is homework 15, which will be the last assignment for the semester. We're going to look again at, of course, we're going to have classes all the way. So we're going to do a very detailed review, and we're going to discuss some further topics. But the material for the exam is going to be completed on Monday. Okay. So in some sense, you have almost 2 weeks, a little less than 2 weeks, let's say 10 days to prepare for your exam. And, you know, I would like everybody to do really, really well. And we will try to make sure that we cover everything that we have seen during the semester. But in any case, why don't we get started with an example like the ones that we have seen before, and meaning an example like the one that we saw last time of a complete heat equation problem, where I would like you to give the details. This is exactly what I asked you to do in the quiz that we had a few minutes ago. So let's, without any further ado, let's see what this would be like. So we want to solve the following equation. The partial derivative with respect to t is equal to 7 uxx. X is between 0 and 2 pi, and t is greater than or equal to 0. And it's, again, the insulated case. So at the endpoints of the interval of the rod, think about it like that. If you like, we have a 0 temperature. And the initial distribution of heat is given by 2 sine of x over 2 minus 5 sine of 3x over 2. Okay? So this is the problem. It's pretty similar to what we did last time. I mean, you know, I'm just playing with the numbers here. That's what the situation is. There's not any significant difference. And let's see the amount of details that we need to give in such a case. So are there any questions before I begin with the solution? Just one of them, yeah. One of them we'll do on the exam, yeah. Mm-hmm. Yeah, if you look at the study guide, you will see that it's one. You will see that it's broken into 3 parts, actually. I will ask you to solve the the eigenvalue problem separately. And then I will ask you to eventually find the function. Yeah, everything is going to be on the exam. It's going to be a very, very nice comprehensive exam. Okay. No, you see, again, it's going to pretty much span 3 problems. So it's not going to be 10. I mean, look at the study guide, and we're going to discuss it. So we'll have plenty of time for that. So let's not worry about it right now. Okay. I promise you that you will have a very, very good idea. Let's try to understand the math behind this problem, and then, you know, we will discuss the procedures for the exam in a very detailed way. So in any case, we want to, we wish to find functions u of x comma t equals to x of x times t of t that satisfy the first 2 conditions, meaning the equation and the first initial condition or boundary condition. You can call them either, actually. So if you plug them into the equation, then what do you get? You get x sub x, x of x times t prime of t is equal to 7 times x double prime of x times t of t, which means that, so here the trick to remember is that the 7 always goes with the t part. That's one of the things you should remember. And you will get x double prime of x over x of x is equal to t prime of t over 7t of t. And now you can see that you have one expression in x, one expression in t. They have to coincide, and they have to be constant. Otherwise, you could change the t, you could change the x, and there's no way those 2 things are going to be the same. I mean, let me make it as plain as, so imagine that you have on the left x squared plus 1 is equal to t plus 7. Do you see why this equation is hopeless if you're allowed to plug in any x and any t that you like? I mean, there's no way this thing will hold, right? The only way that an expression of x, a straight expression of x in x, is equal to a straight expression in t is if they're both constant. So we make them equal to lambda. Here I want you to understand that the book, for mostly style purposes, it has this equal to negative lambda. Okay, I want you to see that there is this small distinction that eventually, as far as the solution is concerned, it doesn't make any difference. So basically you get 2 equations, x double prime is equal to lambda x, and t prime is equal to 7 lambda t. Okay, so we will start with this one. Obviously, it can be rewritten as x double prime is minus lambda x is equal to 0. And the condition, the initial condition, translates to x of 0 is equal to x of 2 pi is equal to 0. Why is that? Because you will have that u of 0 equal for t equals 0. That will imply that x of 0 times t of t is equal to 0, right? Unless you want to eventually end up with the 0 function, you should set, you should have that x equals 0 unless t of t is equal to the 0 function for any t. And that, of course, would essentially negate everything that we're going that we want to do here, because you want to find non-zero function. So here I could have put it like this. Okay, and now this is your eigenvalue problem. So this is a standard eigenvalue problem. You're looking for non-zero functions that satisfy this condition. And how are we going to solve this problem? We just take the different cases. So again, let me write it here so that you can all see it. And then let's repeat its solution. So we start when lambda is greater than 0. If lambda is greater than 0, then the auxiliary equation will have two roots, plus or minus square root of lambda. And the general solution will look like C1 e to the square root of lambda times x plus C2 e to the negative square root of lambda times x. And of course, now the initial conditions will give you that since x of 0 has to be 0, that implies plug in x equals 0. Then with 0 exponent e to the 0 is 1. So this will give you C1 plus C2 is equal to 0. That's one condition. And the second condition, x of 2 pi equal to 0 will give you C1 e to the square root of lambda times pi. Square root of lambda times 2 pi plus C2 times e to the negative square root of lambda times 2 pi is equal to 0. And here we had a very nice trick. Since C1 plus C2 is equal to 0, C1 will be equal to negative C2. So we will have C1 times e to the square root of lambda times 2 pi minus e to the negative square root of lambda times 2 pi equals 0. Yes, but this number here is non-zero, which means that C1 has to be 0. Oops, C1 has to be 0. And hence C2 has to be 0, so no eigenvalues. No eigenvalues for lambda greater than 0. Right? And then we go to lambda equals 0. And we have r squared is equal to 0. R is equal to 0, which means that x of x will be C1 plus C2 times x. Technically, it's e to the 0x, which is the same thing as the function 1, right? And this will give us what? The condition x of 0 equals 0 gives us C1 equals 0. Too bad. And the condition x of 2 pi equals 0 gives us C1 plus C2 times 2 pi equals 0. Both of them, of course, imply that C1 and C2 are equal to 0, and lambda equals 0 is not an eigenvalue. So finally, we turn to the case that lambda is less than 0. Then when you write this equation, this is where you have to be careful. This is positive now. This is positive, right? And exactly because it's positive, the roots of the equation are plus or minus square root of negative lambda. Yes, negative lambda. Negative lambda is positive, right? Since lambda is negative, negative lambda is positive times I, which means that x of x, it's C1 cosine of square root of negative lambda times x plus C2 sine of square root of negative lambda times x. Somebody might ask here, are we supposed to write the whole thing this way? I'm saying, yeah, just write it. Just write the whole thing. I mean, you know, just write the whole thing. X of 0 equals 0 implies what? C1 is equal to 0, right? Because cosine of 0 is 1 and sine of 0 is 0. So you get this equation. And x of 2 pi equals 0 will give you, now that you know that C1 is equal to 0, this will give you C2 times sine of square root of negative lambda times 2 pi equals 0. So finally now you can argue that this has to be n pi, okay, if you want C2 to be non-zero. So, so overall you will have square root of negative lambda times 2 pi is equal to n. Pi is cancelled out, and you will get lambda is equal to minus n squared over 4. For n equals 1, 2, and so on. Okay, so these are the eigenvalues, and what are the eigenfunctions? The eigenfunctions are going to be xn of x is equal to sine of nx over 2 for n equals 1, 2, 3, and so on. For the eigenvalue for lambda equals negative n squared over 4. So now you go back to the equation with the t, and you have t prime minus, what was it? It was 7, right? Take a look. The original equation, it was 7. 7 times negative n squared over 4 t is equal to 0. And this is a separable equation that should be easy to handle. So t of t is going to be e to the negative 7/4 n squared times t. So if we put everything together, then we will have that the following functions: sine of nx over 2 times e to the negative 7/4 n squared over t for n equals 1, 2, and so on, satisfy the two first conditions. And since the first two conditions are linear and homogeneous, that will mean that we can take any linear combination of them, an infinite one possibly, that will also satisfy this condition. And finally, we want to make sure that ux of 0 is what? What did we have? I think we had, let me check it. It was 2 sine x over 2 minus 5 sine 3x over 2. 2 sine of x over 2 minus 5 sine of 3x over 2. So this thing is, so from here, what do you get? You get that u of x comma 0 is c1 sine of x over 2 plus c2 sine of 2x over 2 plus c3 sine of 3x over 2, and so on. Okay, so basically what we're saying is that this has to be equal to that. how can you possibly achieve this? This C1 will have to be equal to this. And this C3 will have to be equal to -5. And everything else will have to be 0. Everything else will have to be 0. So eventually, our solution is going to be, now we can write it down, u of x comma t is going to be 2 sine x over 2. Don't forget now the t term. So for n equals 1, so that's going to give you e to the -7/4 t minus 5 sine of 3x over 2 e to the, for n equals, so you will get 7 times 9 is 63, so minus 63 over 4 times t. And that's the full solution of our problem. Okay, and this is a typical problem of this type. I think I might solve another one during the review, but pretty much this is it. Okay. Questions, please. Okay. So now we're going to try to figure out how we solve the more general problem. So for example, let me give you this problem. So for C2, let me write it explicitly. Thanks for asking this. For C2, since there is no term like this that appears here, that means that C2 is going to be 0, C4 is going to be 0, C5 is going to be 0, and everything else after that are going to be 0. So in this simple case that we just looked at, only finitely many terms are going to be non-zero, and all the other ones are going to be equal to 0. Okay. Of course, the main question here, the pressing question here is, will it be possible to have infinitely many terms that are non-zero? And the answer is yes. And this is where our work today will concentrate. Yeah, you will have to match them. You will have to match them. So in some sense, this sum right here should completely match that one. And the only way you can match that one is if you think of this one as what? As 2 sine of x over 2 plus 0 sine of 2x over 2 minus 5 sine of 3x over 2 plus 0 times sine of 4x over 2, and so on. So the way that these things will match is exactly if the coefficients of the same signs coincide. And there was another question that was answered very, very nicely by 2 of you here, as I see it. So you were asking for these exponents, the 63 over 4, and those come from this, where first we set n equals 1, and then we set n equals 3. Okay, 3 squared is 9. 9 times 7 is 63. Okay? Any more questions, please? No. It's a little t. It's a little t on the exponent. Uppercase t is the function, right? Uppercase t is the function. Little t is the variable. Okay. Any more questions? In this particular case, in this type of problems that we're solving, it will always be negative. And the fact that it's the exponent is negative up there should be welcome because these functions decay very fast and you actually have convergence. So yeah, for this problem, for this specific problem, you will always be getting negative numbers up there, always. Okay, because if you look, let's write down once the general solution that I do want you to remember, but I want you to also know how to get it. So the general solution so this, first of all, the general problem. Oops, this is a t here. Is going to be un of x comma t. I'm sorry, u of x comma t is going to be sum from n equals 1 to infinity of Cn sine of n pi over L times x times e to the negative n square pi square over L square times beta times t. And today, we're going to see, we haven't seen this yet, but we will see that the Cn's are given by some integrals. So they're 2 over L times the integral from 0 to L of f of x times sine of n pi over L times x dx. This is something that we haven't justified yet, but this is what we're going to see today. Okay, so this is your general solution. If you like, this is what you should remember so that you know that you're doing the right thing. I'm asking you to show all the steps. I'm asking you to show all the work. But this is the list that you should remember so as to make sure that you're getting the right thing in the very end. So why don't we take a 10-minute break? And when we come back, we're going to start discussing our Fourier series, okay? Okay, welcome back, everyone. And what I would like to do in this second part of our session, in some sense, at this point, I don't need to connect it with the heat equation or partial differential equations for that matter, but eventually you will see that that's exactly what is going to happen. So, so how do things work here? Basically, our desire is to take at least in its conception, start with a periodic function f from R to R, and expand it as a series of sines and cosines. These are called trigonometric series. And you might argue that they're useful in the study of periodic functions because they allow us to analyze a function in terms of functions over which we have more control. Now, there's an analogy with power series here. So in the theory of power series, you would take a function and you would want to write it as an infinite polynomial. And how did this work? The first thing that you needed to do is understand that if this is indeed the case, if your function can be written that way, then Cn has to be the nth derivative at 0 over n factorial. So the whole process was strictly for functions that have derivatives of all types, of all orders, infinitely differentiable functions, as we call them. So you would understand that this is what you needed, but there was no guarantee that actually this would work. So then you would say, okay, to the function f of x, we assign the power series, this power series, and then you will ask yourselves if it converged and what was the interval of convergence. That's how things work. I mean, there are some examples in which you can find indirect, very clever ways to find those expansions that do not go through this formula. But in many cases, you would just work it out this way. So classical examples are sine and cosine. That's exactly how you would work it out for this. So in other words, what I want you to understand, the general philosophy that I want you to understand is that this is your goal. And you figure out that this is what is needed. So you know that if you can reach your goal, that's how you're going to reach it. And then the question is, do we actually reach our goal? Is it true that when we put these numbers together and we form this power series, that actually that equals our function? And please understand, the answer could be no. Okay, you never saw in Calc 2 an example where the answer was no. I do want you to understand that the answer can be no. Okay, it's not that it's always yes. So I want you to understand that there's a very similar process here. So first of all, there are some things to note. First of all, you can notice that if n is 0, right here for sine, then this is the function 0. So sine of 0x is 0, which means it's a completely useless function. We shouldn't be putting it there. And that's why what people do is they usually write a naught, and cosine of 0x, of course, is 0, plus the sum from n equals 1 to infinity of a n cosine of nx plus bn sine of nx. And there is a very interesting convention here. There is a very interesting convention here that eventually we will give formulas about what the for the ANs and the BNs. And there is a very small technical detail where if we want to give the formulas in a uniform way, in a way that works for pretty much everything, then it's very convenient to do this very strange thing, to put a naught over 2 instead of a naught. Okay, other than that, I mean, you could have put a naught and then you would have needed a different formula for a naught. But if you put a naught over 2, then it turns out that you can write a formula that works for everything. So to each function, we assign such a series. And so this is or I should say, this is the goal in this case. So this is the goal, right? And the answer is what is needed. And when I say what is needed, I mean, can we guess what the coefficients are going to be? So these coefficients, in a way analogous to how we guessed what the coefficients would have been in the case of a power series. In other words, that we guessed this. The method is completely different. In the case of power series, you needed to differentiate and eventually figure out that the coefficients are the derivatives. In this case, you integrate. So just to give you an example, so if I wanted to figure out what this A naught, for example, is, what I would do is integrate from negative pi to pi. You can actually, since we're talking about a periodic function here, you can integrate over any interval that has length to pi. So 0 to 2 pi, you will see that we're going to be focusing on the interval which is centered at 0 for a very specific reason. So bear with me here. If I take the integral of all of these things, then I will get A naught over 2 times the integral from negative pi to pi of dx plus sum from n equals 1 to infinity of an times the integral from negative pi to pi of cosine of nx dx plus bn and now we have a very interesting situation. Okay, a very interesting situation, which is known as orthogonality, meaning you have functions that when you integrate together, when you multiply them and integrate them together, you get 0. And you know what? This whole thing actually is pertinent to the theory of inner products, of the dot product that you saw in Calc 3. This is an actual orthogonality condition that you eventually find. And geometrically, it's justified as follows. I mean, think about it. What is the graph of cosine? Cosine looks like this over from negative pi to pi. Looks like this, right? So you see the part that you have in positive territory is equal to the part that you have in negative territory. So the integral is 0. And then if you take cosine of 2x, it just repeats this motion twice as fast over the same interval. But again, the positive parts cancel out with the negative parts. Same things for the sines. And that justifies why all of these things end up being 0. All of these things end up being 0. And eventually, this integral, of course, is 2 pi. So eventually, if you solve for it, you will get that A naught is equal to the integral of 1 over pi times the integral from negative pi to pi of f of x dx. So that's the formula for f naught. This is in the same philosophy of these formulas that provided us what the correct coefficients should be if it just happens that our function is a power series. Here, this is what A naught should be if it is a trigonometric series. Of course, now the question that comes up is, okay, fine with A naught, how about AN and BN? And the answer is that you need to really repeat the same process, meaning you start with f of x is equal to A naught over 2 with the assumption that this is what you want. And then you multiply both sides with cosine of nx. Or let me say particular, it's not a good idea to use and, let me use k. So a specific k. And here, and now you're going to integrate. So pretty much at this point, you integrate from negative pi to pi. And the conclusion that you get, the conclusion that you reach by doing so is that all the integrals are going to be zero, meaning this is going to be zero, all of these integrals are going to be zero, and here is the nice detail. All of these are zero, with the exception and this is due to some nice trigonometric identities, with the exception that n is equal to k. If n is equal to k, you can easily understand that what you get is the integral from negative pi to pi of cosine square of kx, and this is a positive function. Its integral will never be zero. Okay, its integral obviously will never be zero. It turns out that this integral is actually pi. Turns out that the integral is pi. So eventually you get that ak is equal to 1 over pi times the integral from negative pi to pi f of x times cosine of kx dx. And this is for k equals, interestingly enough, this formula holds for k equals 0, 1. It holds for 0, 2. And also you're going to get that bk. And there's no particular reason why I'm using k here. I use k because I wanted to differentiate in the equation that I wrote. And you will have the same formula for or an analogous formula for the bk's. And that's it. So in other words, this is what is needed. This is what is needed, right? So all now, so in some sense, it's as if we're saying at this point that, you know what, we did our job. That's all we could do. We couldn't do anything else. We reached a point where we said, if we want to have a trigonometric series, then these are the coefficients. Now we can start praying. Well, okay, we're not going to start praying, but we're going to start studying the series that we get this way. So to summarize what we have done is we said we start with a periodic function that has period 2 pi, and you assign to it its Fourier series, and there is no preconceived notion that the series should converge. You hope that it's going to converge. You hope that it's going to converge, but it's a whole different story whether it will actually converge or not. And of course, an, as I said, is 1 over pi times the integral from negative pi to pi of f of x sine of, I'm sorry, not sine, cosine. Cosine of nx dx, and bn is equal to 1 over pi times the integral from negative pi to pi of f of x times sine of nx. Now, what I want you to understand is that these formulas can be made a little more general, if we actually take a function which has period 2L instead of period 2 pi. If it has period 2L, then we assign to it a Fourier series that looks slightly different. It reflects the fact that because these functions cosine of nx and sine of nx have period 2 pi, if you want to modify them so that they have period 2L, then you play this little trick here, cosine of n pi over L times x plus bn sine of n pi over L times x. So by doing so, these functions have period 2L. Can verify quite easily. And now the integrals are going to be an is 1 over L times the integral from negative L to L of f of x cosine of n pi over L times x dx, and bn is equal to 1 over L times 12 of f of x. And this first formula is for n equals 0, 1, 2, and so on. The second formula starts at 1. This starts at 1. Okay. And again, the idea here is that we hope that now this is going to give us a series that converges. And we may ask at this point, is there anything that guarantees that the series is going to converge? So we're going to talk about, so we will assume that f of x is a piecewise smooth function. When I say smooth, I mean differentiable. And so expect its graph to look like this. It can have jump discontinuities. And it turns out that in this case, the Fourier series for such a function converges to f of a if f is continuous at a, and to the limit from the left plus the limit from the right divided by 2, meaning the average of the two limits if f is not continuous at a. Actually, I could have written this formula, and this formula is true always, meaning if it's continuous, then it gives you the value of at a. If it's not continuous, then it gives you some other value. Okay, so in some sense, this formula works all the time. And again, I would like to show you with a graph what this means. So what this means is that at if your function looks like this, then the Fourier series is going to converge right at this number right here. Okay, so this in some sense is the limit from the left. So this is the limit as x tends to a from the left of f of x. And this number right here is the limit as x tends to a from the right of f of x. And the Fourier series converges right in the middle of the two. Okay, it's really a wonderful picture that we have for these functions. Okay, any questions, please? Now, there's one more detail here. And the detail is this, that let me work with the interval from 0 to pi, because this is what your homework is also. And imagine that you have a function f of x that is given just from 0 to pi. So here's your function. It's given from 0 to pi. And which means that you have some freedom of what it's going to be from negative pi to 0. Because you want a function which is periodic with period to pi. And you want it to be defined on an interval of length to pi. You could choose it any way you like, from negative pi to 0. But there are some very interesting choices, because in general, if f of x is even, then think about it. The cosine functions are all even. These are the only things you need. So all the bn's are equal to 0. And if f of x is odd, all the an's are equal to 0. In this case, in other words, we get what is known as a cosine series. And in this case, we get a sine series. And this pretty much goes back to the differential equation that we wanted to solve. Remember that we wanted to express everything in terms of sines, which means that we better work with odd function. But let me just say that if we choose, so this is called the even extension. So this is even extension on the interval from negative pi to pi. And you know that this is going to give you a cosine expansion. And what I want you to understand is that once you define it from negative pi to pi, then you extend it this way periodically everywhere, okay? So in other words, you see, the idea is you start with a small interval, you extend it. Normally you could have started with interval from negative pi to pi, but I told you that our applications here allow us to begin with a function just on 0, on the interval from 0 to pi, which means that we have absolute freedom, and usually we're going to use these functions in a much nicer way. So there is another thing here. So since it's even, all the coefficients, the bn's, as we say, are going to be 0. And the an's are going to be what? They're going to be the integral from 1 over pi, from negative pi to pi, of f of x times cosine of nx dx. Yes, but this function here is even. It's even times even. It's even. And for an even function, the integral over an interval which is centered at 0 is actually 2 over pi times the integral from 0 to pi of f of x cosine of nx dx. So that's the extra nice thing that we're going to be able to have. Okay, so if you look now at your homework in your homework, I'm actually giving you the function x. And when I say I want you to extend it in an even way, I really mean like this. Okay, so basically for next time, what I want you to compute is the integrals from 1 to pi of negative, actually much simpler than that, 2 over pi from 0 to pi of x cosine of n over nx dx. Okay. So these are the integrals that I want you to compute for the homework. And they are, you will need one integration by parts. We're going to focus our attention next time in doing as many Fourier series computations as possible. Yeah, we're going to pretty much repeat everything that we gave today and then look at many such computations. So for attendance, please give me the term that we just discussed for yes series. And that will do it for today. And I will see you on Friday. Okay, please remember, do the correct homework so I have posted all the homework assignments. The one which is due tonight is homework 12. And the one which will be due next time is homework 13. They're clearly marked with their dates on Blackboard. Okay. Have a great rest of your day. I'll see you on Friday.